Today we're going to start chapter 14 on analysis of variance, and this chapter starts on page 643. So in previous chapters we have been covering many things about populations and samples. We started with one population and we collected one sample. With that sample we were able to find values, numerical values, each of one known as statistic, to learn about the population. For example, we were able to compute the mean of the sample, the standard deviation, or the proportion of the sample. We use this information to know more about the population. The way that we did this is trying to find confidence intervals. Confidence intervals were just for us to have an idea where the mean of the population was. So we computed the lower limits and upper limits for the mean, or for the standard deviation, or for the proportion. That was one of the first applications of having a sample, being able to get information about the population. Another thing that we did with the sample, with one single sample information, was hypothesis test. For example, we tested whether the mean of the population where the sample came from was equal to a value, any given value, or was different or greater than that value or less than that value. And we did a similar test for standard deviation or for proportion. So we use one single sample to learn about the population and also to verify hypotheses, assumptions about the population. Then we collected two samples. That was something that we covered on chapter 11, I think. So we collected two samples and we tested hypotheses, like, for example, whether the mean of the population corresponding to the first sample was equal to the mean of the population corresponding to the second sample. The idea was that the null hypothesis was stating that the two samples came from the same population, but the alternative was trying to disprove that. So the alternative was of the kind of being testing whether those two means were different, or one was greater than the other, or vice versa. And also we tested a hypothesis test for these two samples about proportions and also about standard deviation. Now the things are going to be they are going to get a little bit more complicated now, but it's going to be just more of the same. So now we're going to work with the problem where we have a population and we are collecting samples. We initially think that all the samples are coming from the same population, but there might be that at least one is going to come from a different population. We don't know that in advance, so we're going to need to conduct a hypothesis test. The null for this hypothesis test is going to be that the means of the populations from which these samples were collected are the same. So in other words, that all the samples came from the same population. But the alternative is going to be that at least one is going to come from a different population. The methodology that we're going to use now to test this kind of hypothesis, to conduct this kind of testing, is known as analysis of variance. So we're going to have some assumptions to use that analysis. So the first one is that we need to have independent simple random samples from 3 or more populations. We need also that each of the populations must be normally distributed. So we know now how to verify whether a sample is normally distributed, meaning that that sample is coming from a population normally distributed. And also another assumption that we need to verify is that the population must all have the same variance, which we will denote by sigma square. Sometimes we're going to have all the samples having the same size. So that's the case when we have a balanced design, when you have all the samples with the same size. Sometimes we're not going to have that possibility. We might have one sample with a different number of responses at another sample. So that is going to be an unbalanced design. So The steps to solve the problem are outlined in your book. If you go to page 649, you're gonna find this blue table, this blue box. Sorry, the same style that the ones that we have been uh, looking at before in this book. So you're gonna have here the different steps that you need to follow to perform a one-way analysis of variance. So the first thing is that we're going to use the F distribution. So that's the reason this is going to be the F test for one-way analysis of variance. So the once you set your null hypothesis, which is just mu1 equals to mu2 equals to mu3 and so on, versus the alternative hypothesis, which is going to be two or more of the mu's are different. So we're gonna follow these steps. So you're gonna check the assumptions that I just mentioned before. We're gonna have our significant level alpha indicated. Either we are gonna set it or maybe it's given in the word problem. Then we're gonna compute some quantities. Some of those quantities are errors, and other are just different computers that I'm going to give you in a minute. So SSTR, SSE, MSTR, MSE. The purpose of these quantities is at the end of the day, what we want is our test statistic F, which is going to be just the ratio of the last two. So, and then you just proceed finding critical values by using a table, by using a calculator Texas Instrument 8384, or by using language R. So once you have your critical values, you know how to make a decision. If you find your F within the limits for within the limits that the critical value indicates, then you accept or you cannot reject the null. Otherwise, you're gonna reject the null. And also we can use the p-value method that we have been using in the past. But let me show you just a summary in the way that we have been working these kind of problems. The summary is here. So for us to conduct a one-way analysis of variance, as I mentioned before, we're going to set the null, which is just all the mu's are the same, or the alternative that two or more mu's are different. So that is the same as saying that at least one of the samples is coming from a different population. Then we're going to set the significant level alpha, usually 0.05, unless it's something else is indicated in the program. Then we're going to compute the test statistics. So before we have been computing z-scores or student t values or chi-square values, and also we use in the past the F distribution. So we're going to compute the F value by just getting the ratio of these two quantities. Now you have here the definition of those two quantities. So MSTR is just treatment mean square, SSTR is just treatment sum of squares, MSE is just error mean square, and SSE is just error sum of squares. So with these mean squares, we're gonna find F, and every mean square for the treatments, for example, we're gonna use the errors. So in this case, the treatment sum of the squares divided by I minus 1, where I is the total number of treatments. Then MSE is going to be SSE, the error sum of the squares divided by N, capital N minus 1. Capital N is going to be the sum of the all data values, all the responses. So in other words, is going to be the sum of the sample sizes. So all the sample sizes are going to be added, and we're going to get the N, capital N, the total number of responses. And you have here the formulas. If you go to page 648, you're going to find these formulas that you're going to need to use to compute these quantities here. So for example, the treatment sum of squares is going to be N1, which is the size of the first sample, times the mean of the first sample minus the grand mean. The grand mean, I have to write here the definition for the grand mean. The grand mean is just the sum of all the responses divided by the total number of responses. So that is going to be the grand mean. So, and then you're going to square that difference, and then you're going to add the same quantity for the second sample, for the third sample, and so on. So in a abbreviated way to indicate this is just the sum. You use capital sigma to indicate sums of these products. And also SSE, the error sum of squares, is going to be computed by using this formula. So you're going to multiply the degrees of freedom, n1 minus 1 from the first sample, and its variance, so S1 squared, and then you're going to add the corresponding value for the second sample, the third sample, and so on. And also an abbreviated way to indicate that is just capital sigma of ni minus 1 times the variance of the corresponding sample. You can see more about this on page 648. Then once you have f, so everything that you are doing here is just to compute the value of f, your test statistic. We're going to use f to make a decision. So there are two methods. You know that there are two methods. One method is the critical value method, and the other method is the p-value method. So for the critical value method, we're going to use R. We're going to use the function qf, where you're going to enter 1 minus alpha, comma, the number of treatments minus 1, comma, minus the total number of responses minus the number of treatments. So in that way, you're going to get your critical value, f alpha. So if you have your distribution, you're going to need to plot. You're going to need to plot your f statistics that you found here in this step. So you're going to plot, but first you're going to plot the threshold. You're going to plot your f alpha. You know that this is going to be just the value that is going to separate the region that is in favor of the null and the region that is in favor of the alternative. So once you find your value for this critical value f alpha, then you're going to plot f, and you're going to see whether that value ends up on this region or on the other region, and in that with that information you're going to be able to reject the null or not. So the other method is the p-value method. The p-value method, you use directly the statistic f that you found in the previous step, and you use the pf function from R. Remember, you're going to need to use always lowercase letters for the R functions, and you enter the value for f, again the number of treatments minus 1, then the number of total number of responses minus the number of treatments. And again, if you're going to compare your p-value and alpha, and remember, if your p-value is less than alpha, then you reject the null. So it's a lot of steps, it's a lot of work, but you don't need to do all this work. So if you use R, I'm going to show you how to do this with the less number of steps. So we're going to enter the data, and we're going to obtain a table that is going to be a summary of the one-way analysis of variance. Once you read the summary, you're going to be able to find all these quantities here. You're going to find these mean squares, the errors, and you're gonna find f, and also you're gonna find a p-value already in that summary. But the most important thing is going to be our value of f, because once you have f, you can use these two, one of these two commands, and you're going to be able to make your decision. So let's work on one problem. So, and again, just pay attention. The most important part is just entering the data correctly, because if you enter a data value that is not there, it's going to change everything. So the most important part when you solve this kind of problems is accuracy in the information that you're entering, either in your R console or maybe in your calculator or Texas Instrument. It doesn't matter the way that you're going to do your computations. What matters is that you are entering the right values. So we're going to work example 14.4 on page 649. So Let's just read the example first. So we have here our book, and the problem is just that we're going to use the data in table 14.1 to test the null hypothesis that all the means are equal. Use the level of significance alpha equals 0.05. So that's problem or example 14.4. So everything is about table 14.1. So if you go to page 644, you're going to find this table, table 14.1. So that table is about welds used to join metal parts. Metal parts are made by heating a powdered material called flux. In a study conducted by G. Fredrickson at the Colorado School of Mines, 4 welding fluxes with different chemical compositions were prepared. The purpose of the study was to determine whether the welds made from the fluxes would have different degrees of hardness. 5 welds using each flux were made, and the hardness of each was measured in Brinell units. The higher the number, the harder the weld, and the data are presented in table 14.1. So we have here the different fluxes, A, B, C, D, and the different measurements that were obtained for each group. So we have 5 values here: 250, 264, 256, 260, and 239. So the table ends here, so don't look beyond that. So it's just this part. So you can see that the first values that I just read correspond to flux A. Then for flux B, we have 263, 254, 267, and so on. So we have 4 groups, A, B, C, D, for fluxes, and we have 5 measurements that were obtained for each group. So the purpose of the analysis is to know whether there is to know whether there is a difference between these groups. So if we cannot reject the null, then that means that there is no effect of using A, B, C, or D. They're gonna give you the same result. So if you have that one sample at least is not getting the same population mean, then you can say that at least one of the samples, one of the groups, one of the fluxes is performing differently than the other groups, and that's the importance of the study. Then later you're gonna find ways to find which one of the groups was the one that performed better than the others. This analysis is gonna tell you only whether there is one single group or more that are performing different from the other groups, but it's not going to tell you which one is the one that performed better. So that's important. This is an important clarification. The analysis is going to give you only a clue about having to conduct a further investigation. Because if you find that all the means are the same, that there is no difference between one group and the other, then you don't need to go further. But if you find that there is a difference, then you're gonna start looking for the group that is performing better than the other. There are gonna be ways for you to have a clue about the group that is performing better. But in this at this point, to be strict, mathematical speaking, the analysis only gives you a clue about whether a group or one group or more are performing differently than the other groups, or all of the groups are performing the same. So let's start using R. You're going to see now the steps I'm going to follow, and these steps are going to be the ones that you're going to follow. Very, very simple steps. The most important part is enter all this information into R. Once you have this information and you can create a table like this, then you're going to be able to perform the analysis and to get the summary for the analysis of variance, and then we're going to be able to interpret the results. So let me start telling you the steps that we're going to follow when we use R to solve this problem. So we're going to have two variables. One variable is going to be the variable containing our responses. So we have responses. So I'm going to use y. Y is going to be the variable that contains the responses. So we're going to start just entering the data values in the following way. So you're going to write y equals lowercase c, and then you're going to open a parenthesis, and you can start on the next row. You don't need to go directly on the same row. You can just enter and start writing the numbers in the next row. You're going to see why. This is important when you have several columns and several rows. So it's better if you enter the data very well organized. So I'm going to start writing the numbers: 250, 264, 256, 260, 239, and then I'm going to start with the second row. I'm just copying the table that I just showed you a minute ago. So the next row is 263, 254, 267, and you can do this in R now. You can just follow me. 265, 267, another comma, then 257, 279, 269, 273, 277, and finally you enter another row. It's going to be the last one: 253, 258, 262, 264, and 273, and you close with a parenthesis, not another comma. You close with a parenthesis. So now we have the data the data values corresponding to the responses, and the purpose of doing this is because you can compare the values that you just enter with the table, and you need to check that they are the same. So you just compare the table with the data values. So this is just a single data set, but it's distributed in 4 rows, as you can see, and then you just compare to find discrepancy, because any value that is different from the original table is going to change the result dramatically. So you need to be very careful about entering the responses. So that's the first part. We enter the responses. Now we're going to enter these categories, because you can see that the first 5 values, the category is A. Then the next 5 values correspond to category B, and the next 5 to category C. So we're going to enter now a categorical variable. The categorical variable is going to be, in our case, it's going to be X. So this is going to be a categorical variable. And anytime that you enter a categorical variable, you need to use quotation marks. So you can just start with this C, and then you're going to enter the category for the first value. Is the category is just A, so you're going to enter A with quotation marks 5 times, right? Because there are 5 values that correspond to A. So that is going to be my first 5 values. Then you're going to do the same thing with the next 5 that correspond to category B. So you can see that this is a lot of work, but it's worth it, because later you're going to see that you're going to get your answers very well obtained. So then you have values that correspond to category C. So quotation marks are very important for our values. Finally, the last one is D. And we finish with another parenthesis. So imagine that you have now, instead of having 5 elements or 5 responses per group, you have something like 100 responses per group. It's going to be a lot of work, right? So there is a better way to enter this information. So all this information here can be entered in a simpler, in a better way. So I'm going to give you now the other way, the one that is easier. So we're gonna enter now our values in the following way. We're gonna enter. So this is just for you to know what we are doing, but in R, you can just enter X equals lowercase c. And now I don't want to repeat 5 times A by hand, so I'm going to write rep for repeat, rep, parentheses, and I'm going to tell R that I want to repeat quotation A in quotation marks 5 times. And then don't forget this comma. Then I'm going to repeat V with quotation marks also 5 times. And you don't have to have the same length for every sample. Remember, if you have an unbalanced design, then you're going to have groups with 3, other group with 4, another group with 20, and so on. And then this is very important, the way that you enter the information. So then we have rep to repeat category C 5 times. And finally, I'm going to repeat category D 5 times. And this is the last one. So instead of a comma, I need another parenthesis that matches this one. So that's what we're going to do instead of doing this. So this is a shortcut to do our work, to enter those categories. Once you have the shortcut, then we're going to create the table. So we're going to write my data. That's a name that I'm just using. You can use any name. So, and this is going to be created by using this command in R, data dot frame, and then you enter the columns. The first column is going to be my categories. The second column is going to be the responses. Then I'm going to create a linear model. So I'm going to give the name my linear model, and it's going to be by using LM, lowercase, remember, LM, parentheses. I'm going to say that Y is going to be a function of X. I'm going to use tilde. So tilde is in your keyboard usually to the left of the number 1. Is you need to use the shift key to get tilde, and then you just write here X, then a comma, and then you're going to give the name of your data frame that is containing this information, which is my data. And finally, we're going to call ANOVA, which is the command that is going to perform all the computations I mentioned before, the errors, all the mean squares and everything, and F, and even the p-value. It's going to compute a lot of things just by using ANOVA, and you write here the name of your linear model, my linear model, and then you just read the results. So we're going to analyze the data. So read results. Especially you're going to copy the values for F, and if you want you can use the p-value, but it's very just working with F. So let's see. I'm going to enter all this information into R now, so you're gonna see just the difference. So let's move on to R now. So I have here this information to be entered into R. So I have here my R console, and I'm going to enter now everything. Okay, so I have here my responses, my categories. Anytime that you enter and you haven't finished your command, R is going to give you a plus sign, meaning that you can continue entering information. So that's the only meaning of this plus sign, is that it's an unfinished input. Then you just close, and then you get the usual prompt from R. So the same thing when we are enter the categories, then my data, my linear model, LM, and the ANOVA command, then enter, and then we get the table. That's the important thing. We're gonna just, you have here the different values, the mean squares, the sum squares, degrees of freedom, and the F value, and the P value. You have the P value, you have the F value. So we're going to compute both. The F value is just 3.8734, and the P value is 0.02944. So that P value, we're going to check. That usually is the P value corresponding to the 0.055 significant level. So we're going to check now to see whether we are correct or not. So let's continue with our work. So now from that table, the only values that I was interested in was my F, the F value, and the P value. Now we're going to check whether this P value corresponds to an alpha of 0.05. So with the F value, we can do two things again, remember? So we can use the critical value method first. So the critical value method, so meaning that we need to find the F, so the critical F. So the critical F, we need alpha. Alpha is 0.05, was given the problem. So our alpha, remember, is going to be something like this. This is alpha. So we're going to find that F alpha by using QF of, then we have 1 minus alpha, then I minus 1, and capital N minus I. So what are these values? So these values are, so we have QF 1 minus 0.05, comma. What is the number of treatments of groups? We have 4 minus 1, and the total number of values is just 20 values. 20 values minus 4 groups. So that's what we're going to write here. What we're going to enter now into R to find the critical value F. So let's do that now. So let's go back to R and do this computation. QF of 1 minus 0.05, comma 4 minus 1, comma 20 minus 4. So this is 3.23. So F alpha is 3.23, 88, 72. So let's write that down into our notes. So we have now F alpha being 3.23. So now we're gonna plot. This information. So this value goes here. So that's the limit of the threshold. So F, the value that we have for F that we found in the previous step, just by reading the summary table from R, is 3.8734. So that value goes where? Goes to the left or to the right of this critical value? Is going to go to the right. So it's going to be in the region that rejects the null. So we're going to reject the null. So that's the conclusion by using the critical value method. So let's work the P value method. So for the P value method, we need alpha again. Alpha is 0.05, and we're going to find out our P value by using PF of 1 minus alpha, comma I minus 1, N minus I. So this is going to be PF of 1 minus 0.05, then again 4 minus 1, comma 20 minus 4. So let's enter this information into R now and see what happens. So R is here. So I'm going to write now PF. I'm going to type PF of 1 minus 0.05, 4 minus 1, 20 minus 4. So we're going to find a value. Oh, there is a mistake here. So what I need to do is 1 minus PF. Sorry for the mistake. Is 0.05, 4 minus 1, 20 minus 4. That's the proper formula. So it's gonna be, okay, I need to stop this for a moment to check these mistakes. Okay, the formula is 1 minus PF of F. So my mistake was I was using alpha again, but when we are computing the p-values, as we did in the past, we need the test statistic, not the significant level. So it's 1 minus PF 3.8734 was the value of F that we obtained from the table. Then I minus 1 is just 4 minus 1, and n minus I is just 20 minus 4. So the answer is 0.0294. So I'm going to copy that information in our notes. So and that was the mistake I have in my formula. So anytime that we compute the p-value, we use the test statistic. So not alpha. We're going to use alpha to compare to the p-value. So for a moment, I was just working in the same way that I was working the critical value method. So this is my test statistic, the one that we're going to use from a previous step. So if you do that, we're going to find this value, which is also the value that we found from the table. Remember, from the table, we found F, and we found a p-value. So the p-value that is in table is actually the value corresponding to alpha equals 0.05. So the final step then is just making a decision. So we're going to make a decision in this case by using the p-value method. So we have our p-value is just 0.0294. Alpha is 0.05. We compare this and you see that the p-value is less than alpha. So again, you reject the null. So if you reject the null, you're going to say that there is enough evidence. There is enough evidence to reject the null. So there is at least one treatment that performs significantly different than the others. So that's the final conclusion. So now you're going to have the opportunity to play with this. You're going to solve problems from the corresponding exercise set. So I'm going to give you a couple of problems to play with this method. And then we're going to have a last session the next time, which is going to be about two-way analysis of variance. So it's going to be, that is going to be the last thing that we're going to cover in this semester. So you are almost ready to finish the semester. So that once you complete your classwork and homework, we're gonna have a review session for the final exam. So we have section 14.1 exercise set on page 657, and you're gonna solve problem 18 and problem 22. So two problems. So you're gonna solve those problems and you're gonna upload your results into the corresponding classwork section on Canvas. So problem 22 is problem 18 first is here. So I'm going to give you an opportunity to see the information. It's about life-saving drug. Penicillin is produced by Penicillium fungus, which is grown in a broth whose sugar content must be carefully controlled. So several samples of broth were taken on 3 successive days, and the amount of dissolved sugars in milligrams per milliliter was measured on each sample. The results were as follow. So you have 3 treatments, day 1, day 2, and day 3. So you can use again for categorical variables, just A, B, and C. And that might work. You don't need to use different categories. You can use day 1, day 2, day 3, as long as you use quotation marks. Any way that you can use to identify any group is fine. You can use just group 1, group 2, group 3, or G1, G2, G3. The category, the label is not important, as long as you use the same label for the group, for each group, for, the label, a different label for each group, then you're gonna be able to find your solution. Then part A, construct an ANOVA table, is just follow the steps that I just show you to get your summary table, and then you're just gonna part B is just you're gonna conduct your testing. So you're gonna use either critical value methods or your p-value to make a decision. So that's problem 18. Problem 22 is about floods. So rapid drainage of flood water is crucial to prevent damage during heavy rains. So now you have several designs for a drainage canal were considered for a certain city. Each design was tested 5 times to determine how long it took to drain the water in a reservoir. The following table presents the drainage times in minutes. So now you have 5 different categories. They are number 1, 2, 3, 4, and 5. You can use again letters A, B, C, D, and E, or if you use the number, just enclose the numbers in quotation marks, and that is going to be fine. So you're going to do the same. You construct an ANOVA table, and in part B, you just make a decision by using alpha in this time equal to 0.01. So the value that you're going to get from the summary table is not going to be p-value for 0.01, it's going to be p-value for 0.05. So you better compute your p-value by using the formula that I used at the very end, the one that I made a mistake because I was looking at the different part of my formula sheet. So that's all for today. So send me those problems, and we're going to continue next time with another with the final section, chapter 14, and that's it.